on the processor that correspond one-to-one with the interfaces on this RTL. So just as you had data input streams here, you have data output queues on the processor, which hook up pin for pin, any width, up to 1,000 bits wide. So if you had 384-bit data path stream going into that RTL block, you would specify a 384-bit output queue here, such that you can control everything that's happening on the pins of this RTL block, cycle by cycle, from software, with full debuggability, with full modeling of this interface in these higher level tools. And that's a very important element of efficiently serving the bandwidth requirements of this RTL block, and of providing essentially a higher degree of programmability, controllability of what this whole subsystem is doing than in a traditional model where this RTL block worked alone, or this RTL block was simply hooked up to a bus and some remote processor was attempting to reach across the bus to feed it the necessary data. A couple of side notes here. One of the things that this gives you is now a very consistent way for data to flow from system memory in and out of this RTL block, because the processor, in a sense, becomes the smart DMA controller. And a single processor has enough bandwidth, particularly given its wide instruction capability, to manage multiple RTL accelerators. I'm not going to go into detail in this example, but the idea here is that fundamentally you can think of a processor as the programmable glue that holds together multiple hardwired data paths that may be used within that design. So that if this was some FFT engine, and this was an FIR filter block, and this was some Viterbi decoder, let's just say hypothetically, you could actually specify an instruction set of a processor which is able, in every instruction word, to read and write memory in one port, do a second independent read of write of memory, process data in and out of RTL block A and B and C, all in the same instruction, but all independently scheduled. Where, for example, here, each of those operations was 128 bits wide. In fact, this is the full description of the processor that does this. So this is all that you needed to specify all of these interfaces and all of these new instructions. I won't walk through the syntax for you. I'll spare you that. But it should get across the idea. It's a very powerful computational engine here that we've created, which is doing all of this data shuffling among these different RTL blocks, streaming data in and out of all of those blocks simultaneously, doing, roughly, 1,500 bits per cycle of data transfer, and all rather concisely described in this little piece of description here. So, integrating legacy RTL blocks is just one way to have these very high performance computational subsystems with a degree of programmability. But you can also use that same instruction extension mechanism to actually incorporate the accelerators completely into the instruction set, completely into the software tools of this processor. So that you can think of extending the processor such that these data paths, analogous to the data paths that we saw in that RTL block, are now data paths and instructions of the processor itself. They still may be highly idiosyncratic to the particular task at hand, but they are programmable, they are inside of the simulation model, they are visible to the compiler so that you can write an application that uses all of these new functions. So if you need to do functions that have 64 7-bit multiplies per cycle, you would describe those in the TIE instruction set, and you could complete those 64 7-bit multiplies every cycle, as needed by the particulars of your algorithm. The advantages here is that you can have any number of new data pipelines, registers, memories, interprocessor communication channels, so that you can do the equivalent of hundreds or even thousands of operations per cycle. That this TIE format is very concise, probably 10x more concise than the equivalent Verilog. And the cycle-by-cycle behavior of every accelerated function is written in standard C. It's modeled in the fast cycle accurate simulator. It becomes part of the system model automatically, rather than requiring separate modeling or simulation at the very slow RTL simulation speeds. Now, what we do when we have this kind of capability is then build, among other things, various kinds of DSPs. So, of course, we open up this language so that our customers can specify the custom DSPs that they want to do with any number of operations per cycle, limited really only by the computational requirements of the application. But many customers don't want to start from scratch. They want to start from a well-established architecture. And Tensilica, therefore, offers really as part of this same environment a wide range of DSPs at varying levels of performance. They start from very small, really FIR filter accelerators, dual MAC, quad MAC, 8 MAC, and 16 MAC per cycle designs representing the broadest range and the highest performance of any production DSP core in the industry right now. The Connex D2 is just recently announced in the last couple of weeks as a new family. We announced the Connex baseband engine as a flagship several months ago and is already in silicon and is quite a popular building block, especially in the computationally demanding applications like LTE. And I'll talk about a design based around the baseband engine in a little bit. Let's now do a little bit of Gray's Anatomy on a DSP here. So this is a modern high-end DSP, and it shows both its computational units and its register resources and its memory bandwidth. So it has multiple memory references per cycle, each 128 bits wide, general purpose register file, large vector register files internally. Each of those vector register files is operated on by an array of execution units, effectively making it a 4-way, 8-way, 16-way vector operations. One of these vector operations can be as complex as a radix 4 butterfly or a complex multiply, which is, typically 4 multiplies and a bunch of adds, so that you can do a radix 4 butterfly per cycle, or 4 complex multiplies per cycle, or 4 FIR filter taps per cycle, or 16 real FIR filter taps per cycle in this machine. I will not walk you through all of the details of the instruction set, but just to give you some of the highlights, you start from a baseline instruction set, that general RISC instruction set, which is configurable up to about 150 different operations. And then seamlessly layered on top of that is complete DSP instruction set capability, not in any way limited to the notion of RISC. So this does very wide instructions. It does multiple vectors every cycle, so that you're theoretically able to do close to 100 operations per cycle in this DSP instruction set. And it includes rich loads and stores, lots of different flavors of complex and real number multiplies, lots of different arithmetic operations, and a bunch of other rather interesting operations. single cycle radix 2 and radix 4 butterfly, 8 integer or fractional divides in a cycle, 4 reciprocal square roots in a cycle, arbitrary permutation and selection among vectors, and the like, so that you can really do a very wide range of parallel operations just by programming in this standard instruction set. And to give you an idea of some of the performance capabilities, because you're able to have this very high memory bandwidth and lots of operations per cycle, you can do extremely well on things like FFT. So, for example, if you take LTE, which in a MIMO situation requires a receiver to do multiple 2K point FFTs on every symbol that comes down the path, you're talking about being able to do the FFTs so fast that a single baseband engine can do all of the FFTs required using only about 20 to 30% of its frequency, depending on what process technology you're doing, which means that that same processor has plenty of extra cycles to do many of the other processing tasks that are required in LTE. And you may need more than one baseband engine for extremely high performance applications. This is what we would see probably not so much in a single LTE handset, but in LTE Advanced or in a femtocell, picocell base station environment. You may have a requirement to really scale the performance. And so you can put, for example, 8 of these engines together such that you're doing 128 multiply accumulates per cycle. Something between 600 and 700 basic ops per cycle. You could do almost 1 million 2K FFTs per second in a cluster of 8. And this shows how these cores are linked together using these streaming interfaces, which effectively creates a shared memory cluster where all of the processors see all of the memory in a coherent fashion distributed across the cluster, which leads to a very easy programming model for all of these engines. So what we find when we think about now the vocabulary of design for LTE is a pretty wide continuum of choices. And they really reflect different points on that continuum of where you want to be in generality and flexibility versus efficiency and specialization. So at one end of the spectrum, you could find that using 1 or 2 of these baseband engines might be the right answer. You could start to add accelerators, where those accelerators could be either hardwired blocks, which are plugged in using these extended interfaces, or they are new instructions, specialized instructions added to something like a baseband engine. Or you could say, well, I want to do relatively more of my work in the accelerators, and I downsize the DSP. In fact, I could downsize it to the point where it's really just a controller. It's not doing any significant DSP operations. And finally, you could say, well, I can configure very small processors. These are now available in high performance configurations at less than 15,000 gates. So you're talking about something which in current technology is maybe 2/100ths of a square millimeter of silicon for this kind of small controller. And at which point you've now got really local programmability of all of the characteristics of this accelerator, whether the accelerator is written as instruction extensions or hardwired logic. And so many designs we see in LTE handsets, and Tensilica has multiple design wins in LTE handsets today, use some combination of these styles, including this style of distributed localized control with acceleration. So one of the things that has been the real test for not only this processor technology, but for everything we're talking about in methodology, is this very important program in Tensilica of putting it all together, really going out and building an LTE terminal baseband PHY. And so I'm going to give you a little bit of a snapshot of the development architecture that we've been working on, which reflects this design style and is intended as a realistic design for implementation of LTE in the very demanding Category 4, 154 megabit per second MIMO OFDM solution at modest power levels. So I won't walk through all of the features here, but we really have something which is implementing the key requirements in terms of handling all of the resource sharing. It's really using what we call block adaptive pipelining. That is, where we really are streaming the data all the way through without significant buffering, so that it does not require significant amounts of memory. So this whole design requires less than 500 kilobytes of memory, which is not much given the level of complexity of this. And something which runs at modest megahertz in a low power process. We can generally think about this partitioning into 4 domains of operation. There is a signal domain, which is really at the front end of the receiver pipeline. There is call it the matrix domain, in which we're well, so signal domain is sort of how you get from the time domain, which is how signals come in off the antenna, into the frequency domain. How you get from the frequency domain to soft bits, that is, bits that still have essentially a built-in weighting as to how well received they have been. And then you get from soft bits to bits. That's really what goes on in forward error correction. And then the control domain, in which you're setting the modes for all of the above. I'm going to highlight this turbo processor because it's a good design example of extremely specialized design, which rivals the performance of hardwired logic, but which is doing it in a fashion which is a much more flexible than the traditional approaches to forward error correction. So this is a block diagram of this LTE PHY. And what you see here is 3 baseband engines, 1 in the transmit, 2 in the receive, which are doing different parts of the signal processing and the matrix processing. There is a very complex protocol in LTE for HARC. That is, it actually only transmits a portion of the bits, and then, depending on whether the signal could be correctly reconstructed by the turbo decoder from this subset of the bits, it may request more bits be sent back. It may make a request through the transmitter back to the base station, which will send some more bits, which are then combined with the original bits, and then a second attempt is made to extract the original data stream from that. And this iterative process works at 2 levels. One, there are iterations within the turbo decoder to attempt to determine whether a clean version of the data has been received, and then a second level of iteration in which more and more of the original bits are transferred depending on how well it was received.
Chris, how much latency does that add?
It all has to fit within fairly tight latency controls, so that there is. This is operating in pretty hard real time, but it's overlapped, so that you're.
Right. I'm asking the question: does it support voice right now, or is it more of a data problem?
I don't know. exactly what the interactions are between voice and this HARC protocol. The HARC protocol, I don't think, is fundamentally different from the HARC protocol, which is used in 3.5G.
Okay.
And so I don't think that it is incompatible with the requirements of voice. You're really only talking about,
Nanoseconds.
well, I mean, I think you may be getting up into the millisecond range, but not tens of milliseconds for that whole dialogue. So one of the things that we've done as a demonstration, as an experiment, and as a useful engine is to build a turbo processor. And LTE is a really hard problem, about 6,000 ops per bit. But we use the full set of tools, wide data paths, wide instructions, multiple wide memories, to build a turbo decoding processor. And in fact, to give you an idea of what this looks like, I'll go on to the next page. But we looked in the literature at the effective gate count of different proposed solutions for turbo decoding, scaling them all to this 154 megabit per second throughput rate. And what we find is actually this processor-based solution is among the smallest of the proposed turbo decoding solution, which implies it should be among the lowest power of the turbo decoding solutions. So here it is, a programmable processor, albeit a very, very specialized processor, which is beating the hardwired logic designs for this. If we look inside of this, and I won't belabor it too much, is that we have a wide instruction which is doing multiple load and store operations every cycle, as well as doing this very complex state update process, called the alpha computation and the beta computation. In a single cycle, we make 6 different memory references. And it's massive single instruction multiple data. So we're updating a bunch of states. It takes about 21 8-bit operations per state update. There are 8 states per window. We actually do 2 successive bits. So we do 8 state updates and then another 8 state update. There are 8 windows operating in parallel. So the ops per cycle is about 2,600 ops per cycle. And so we effectively do this, taking an average over the multiple iterations of about 3 cycles per bit. You have to go around this loop 6, 8, 10 times in order to converge on the correct solution. And I'm not going to walk through this, but in fact, you write the inner loop of this turbo decoder in C, albeit with some specialized operations. So the beta computation becomes an intrinsic function. These read operations become intrinsic functions, but otherwise it looks pretty much like standard C. And what happens in the inner loop, it unrolls this loop. In a single cycle, we do this entire loop in one cycle. So it loads systematic data, parity data, it reads interleave addresses, it reads states, and it updates the states and writes the next state information continuously. Now let's talk a bit about methodology. Let's think about the larger context of how you go through designing such a complex system. Now, first of all, you're going to be working in algorithm design. And this is the place where things like the Synopsys System Studio or MATLAB might be used to determine what each of those functions is. This is the place where the steepest descent model starts, where you really have to, this is where all that math is that determines what are those operations. But that's just the starting point for an implementation. The next thing you're going to do typically is start refining that algorithm by doing a fixed point implementation. You may be doing that fixed point implementation within System Studio. You may be going from the world of algorithms to C code and running on your host, running on your PC, for example, the fixed point C implementation of each of these algorithms, and continuing to use this system model, which is typically starts as a floating point model, as the reference. And so you're checking for accuracy. You clearly, at this point, want to restrict the bit resolution as much as possible, because narrower bit resolution generally is going to mean higher performance or smaller hardware. And there's a number of things that we do here I'm going to talk about in a little bit to facilitate that. Now you have fixed point implementation, typically in C, and now you want to start partitioning that. You're going to say, okay, well, function number one, I'm going to leave in C and I'm going to map it onto one of these DSPs. Function number two, I may say, this really is going to benefit from special purpose instructions or special purpose hardware. I'm going to map that onto an accelerator. I'm still going to drive it from C, but some of the computational implementation is now leveraging specialized instructions. And I may do this for several different subsystems. This might be, the front end, which does the frequency offset, FFT operations. This might be doing the MIMO. This might be doing forward error correction. And this is a place where the exact trade-offs between what's in the accelerator, what's in the DSP code, become critical. And this is where some of our tools, our fast instruction set simulator, our cycle accurate simulator, our tools for extension of the processor play a central role. Now, you've broken it up into pieces and you have to put it all back together again, because you don't really know if it all works until you've hooked up these subsystems to buses, you've hooked them up to peripherals, you have the whole data flow from end to end through this. And that's where these tools, the Synopsys integrator, the Tensilica XTSC System C model, and then there's some other tools like from Coware and Carbon and others, which represent tools for pulling all these pieces together so that you can verify both the hardware and the integrated software across this spectrum. And then finally, you need to take this integrated model and actually build it. That is, you will typically be mapping it perhaps into a prototype FPGA environment where these blocks now have to be all synthesized together. You're typically going to be building an SoC or an application-specific IC, so you're going to generate RTL and you're going to go through synthesis and place and route. And so all of the tools for FPGA and SoC synthesis and place and route and simulation come into play. But this is sort of a picture of that refinement process which takes place. Now, so let's see how this maps to this kind of a picture here. So we're going to talk about how these things come together. The high-level tools like System Studio with models like those from Steepest Descent are really the tools for deciding on the right algorithm. And then you want to optimize that algorithm, find better algorithms. You may be doing some of the fixed point conversion at this stage. That is, you're putting it into the architectural context because you're understanding what is it that my underlying hardware, my underlying processors, what are their strengths and weaknesses, how do I have the minimum computational cycles or minimum area associated with that. And that's where I will then start flowing into a hardware-software implementation where I'm now going to be partitioning among multiple processors, partitioning between processors and blocks of hardware, and starting to worry about some of these upper layers of, for example, how does my control software talk to the core Datapaths software. So that partitioning is often going to take place inside of the Tensilica tools. And then you want to start putting it back together again. Here you split it up in order to be able to understand each of the subsystems. You've now got functional subsystems, and you have to see that those functional subsystems add up to a functional system. And that's where the integration environment, sometimes in System C, sometimes in more complete modeling environments like the Synopsys integrator play an absolutely critical role in ensuring that you can take individual subsystems and with minimum effort show how all of those subsystems sing in harmony together. And then you've got optimization that you do there, because always you discover some things that happen. You may say, oh gosh, I don't have enough bus bandwidth here. I need to go back and re-provision my buses so that they're wider buses. Or I need to create a dedicated queue path between one processor and another in order to offload the bus. Or I may say, you know, this bus is too wide. I'm wasting too much hardware, because when I finally integrate it, I find that I really don't have that much data traffic moving between subsystem A and subsystem B. And those are all critical parts of how you converge on something which is fast enough to implement the necessary functions with some headroom for surprises, and at the sort of hardware level where you're willing to carry around the battery that's required to power it. There are some very interesting interactions that take place here. You know, really starting from this notion of the reference architecture is really always the place we start. And this one's working now. And you have, typically we find that once you get to a fixed point implementation, and sometimes even while still just purely in the floating point domain, you'll start profiling that to discover the hot spots. Then you may find that allows you to optimize the algorithm, but that may also allow you to start specifying how the instruction extensions can be used to make a more capable processor. That is then used to create models of the individual instructions, which can be used on the host for augmenting the C simulation of that, the C execution in conjunction with this optimized algorithm. So then you can validate performance, validate function. You can use the same extensions to create the RTL, and then you can do RTL integration. So then finally we just wrap up showing you some of the pictures of how the pieces fit together here, where we've got now the integration of the Tensilica tools into the Synopsys Innovator environment, where we have the model of the processor core combined with all of these other building blocks that are in the Synopsys library, where you can then adapt it to the other building blocks. You can do transactions between the low-level processor interface and a transaction-level modeling interface. You can even drive scripts through this in order to stimulate the behavior of the system. Here's a picture of how you can debug the instantiation of a particular core within this environment. So you've got all of the information for debugger attachment. In fact, it's very simple to attach the debugger to one of these running models. And therefore, you can have all of the experience of classical host-based debugging, but now you're doing it for each of the multiple processors that you find within one of these complex platform designs. And this ability to debug seamlessly with these augmented processors running in conjunction with models of the other low-level building blocks is a very important part of having a very efficient design. So you get the console, you get the debugger, you get the structural representation of it. So just to mention the things that I've walked through today, we've talked about fundamental baseband trends. We've talked about the data plane processors. What are they? And what are the ways that you reach for performance? Because this is the only way in which you're going to build efficient hardware-software solutions. We've done a bit of a drill down on an LTE reference architecture and a very specialized turbo decoder. And we've talked about methodology, how we flow through from this very high-level model, the algorithm design phase, fixed point representation, mapping into subsystems, integration of subsystems, and generation of the real implementation for the final hardware, which is going to go into silicon. Thanks. Questions?
So I think we're good right now. I think we need a break.
Yeah.
So I'll continue. I think the break kind of happened naturally.
Yeah, right.
So when people come back, I'll do a very brief.
Well, how about we do 10 minutes and then
10 minutes and then
A little bit about the challenges, the computational complexity of the algorithm, some of the implementation choices. Synopsis is here because we are, if you will, the glue helping to bring these different components together with respect to tools in this domain which utilize the algorithms on the one hand and model the processor. So Chris was referring to things like fast ISSs, which are the fast instruction set simulators, and we are on our side providing solutions to integrate them. So let me talk about the outline a little bit. I'll talk a little bit about the challenges, but only very briefly, because they have been very well set up by Frank from Steepest Descent and by Chris. I'll talk about the optimization components, the optimization potential here across hardware and software, and then talk about the software development aspects, verification aspects, some architecture analysis aspects, and then a little bit of about the ecosystem, why we are really here at the end of the day, how these things fit together. So if I look into a phone, and I apologize, I've been using this for a while. It's not the newest phone certainly, but some of us may remember it or even still have. What is it, the Trio or something? So one of the challenges, if I look into my application processor in here, is how do I develop the right signal processing algorithms, implement them, and then bring them to the actual chip implementation flow. So this is the domain where we overlap with Steepest Descent and where we take their algorithms to go to implementation. The other big question mark for the poor designer here is how do I get a model of that for my software development team as early as possible? The challenge being that for a semiconductor developer like a Qualcomm, a Broadcom, a TI, Freescale, what have you, the software has become the long pole. Even if they develop the chip, if the software is not up and running on it, then they have no really ramp up of revenue to see it. I'll talk about that a little bit later. So let's talk about the algorithm optimization first. So that's the overlap and the juncture to the Steepest Descent portion here, where you really have the designer, the poor guy with the question mark on his head. He's asked by his boss, well, create an algorithm and meet key requirements with respect to bit error rates, signal to noise ratios, word lengths, quality, sync speed. And that goes back to your question earlier, Carl, in terms of how much time do I save? If this guy would take the book, take the standards, start writing C++, you'll add a significant amount of time to it. So here, he's basically now challenged by more and more of this, so he needs to be very efficient. He needs to be very efficient to deal with the complexity, so he needs to be efficient in modeling and simulation performance. He needs to be able to look at things, and he needs to be able to then deliver, as he's the algorithm dude, he needs to deliver to the guy who actually has to implement the silicon and implement the RTL. So that's where this comes in, this model-based design. The designer really wants not to start from C++. He wants to basically start with a model-based design environment, which is this model-based design where we pointed to the different blocks, which the team from Steepest Descent has developed. And I like Chris's flow description. This is a domain where we just want to get the algorithm right. We wanted to make a certain coding transformation and so forth. So that's the designer's wish. The three main components which the designer needs to deal with are performance. So if you look into the number of simulation cycles, the number of points you need to execute, And remember, this is long before the actual chip is available. You need very high speed simulation. You can't wait forever. That's where those different abstraction levels come in, which Chris alluded to a little bit, where you have less accurate but very fast models of their processor, and then later on you have more accurate models. Same is true for algorithms. You will have, for the fixed point simulation, our businesses, as I mentioned earlier as one of the questions, we are the Ferrari of simulators, so we have the fastest engine. So we have done a lot of work to optimize the simulation of fixed point, for example. Once you have decided you want it in an 8, 9, 11 bit width, we have done performance optimization on that. The second aspect is productivity, and that goes really directly as answering Carl's question from earlier. With model-based design and having models available, having IP available, you don't start from scratch. You don't start writing your C++ from the book or from the standard. And you need analysis around it, so you want to look at visualizations like the charts which Frank showed, where you have early on the ability to know in which part of the spectrum you're working right now. And then the last thing which you need to be integrated with the rest of the flows. Nothing can happen in isolation. If the algorithm dude would be just doing the algorithm work and tell then the design team, well, here it needs to be 9-bit, over here it needs to be 11-bit, it would be a waste if those models couldn't be reused later on for verification. And that's what Frank pointed to, having reference models available and using those for verification for downstream code generation. So let's start with the productivity portion and talk a little bit about the requirements of what users are looking for from a tools perspective, right? So the alternative is you can do all of this in C and C++ by yourself, but you will spend a lot of time on infrastructure components totally outside your core competence, because the objective of the algorithm developer here is to get the algorithm right, to optimize it. So he wants to really take the textbook, enter the blocks he gets from an IP library, from a model library, focus on the algorithm itself, and then put design checks in here. He wants to have block-based design. So ideally, I take my filters, I take my blocks out of a pre-existing library, put them all together, and then connect them, even though if those connections, as Frank pointed out, can be very complex animals. There can be matrices of different size going back and forth there between the different blocks. You also want to be able to manage your design team. So from an implementation perspective, all this needs to be very well integrated with things like revision control, scripting environment, so that you don't do just your sketchbook and your notebook which you deliver to the next design team, but you have something which you can hand over, which is executable and well integrated. So for model libraries, you need, for most simple things like filters and small data sources, you need all the way to channel models and complex analysis models, those items from a library. So that's what Chris pointed to in one of the discussions earlier. The environment in which the design lives becomes your test bench, right? So you have your whole channel model, and you figure out if LA decides to put up some more skyscrapers, what does it do to your channel given the current infrastructure you're living with? On top of it, you want to have things like reference design kits, and that goes back to the original question, why do you not do it in C++? If you have a standards compliant reference of those standards, you have a huge jump start here to get to the design earlier. So here is this example library, and I, in the interest of time, won't go into too much detail. That's the same graph which Frank used earlier, where you have the channel coding, the scrambling, and then the mapping, the pre-coding, all the way to the OFDM modulation at the end of the channel for the transmitter. And for all these blocks, in an ideal world, you just take those, drop them, connect them, configure them, and get your simulation to find out what certain parameters in your design do to your performance and to your overall algorithm execution. So this is the library for LTE, for example, needs to be able to deal with verification of the algorithms. You need to be able to create tests. You want to be able to communicate with the rest of the design team. If I do this at the input, this is what the algorithm does. So that's both a learning and then also a verification experience. You want to be able to generate test models, use it as a golden reference, and then do bit error analysis. So we have customers who use tools like this to basically every night run thousands of simulations to generate bit error rate curves depending on the latest changes they have made to the model. So this is where we interface to steepest descent. That's the juncture where we have as our core competence to get you the Ferrari engine of simulators, and steepest descent has a core competence to get you all the algorithm expertise, and we are simply working together on that, combining our core competencies. So the file library highlights, I'm not repeating that, what Frank already said, just the highlights here. We are tracking compliance with release into release 9, or with release 8 into release 9. It's supporting several antenna transmission types, including all the MIMO layering and pre-coding options, and it's going through the data and the control channels of the algorithm as explained by steepest descent.